Even be talking about this, but I can't help myself. This is a little board that we've made for 3 or 4 years. It's called the EVTV CAN Due. And the reason it's called that is it's like an Arduino Due, which has kind of fallen out of favor. It had some weak points, I suppose. It was limited to 3.3 volts in an Arduino world that was mostly 5 volts. And it had no EEPROM. The original Atmel chips they used had EEPROM built into it, 4K. Why do you need EEPROM? When you load a software program into your board, inevitably there's going to be configuration items. I just don't write any software that you can't configure to do something, and you don't want to enter that every time the thing runs. If you want it to charge at 14 amps, you want it to do it every time it comes up, and you don't want to have to supervise it. So you need to be able to write persistent data to variables that are persistent. The Arduino Due was a SAM3X, and it's 84 megahertz, 32-bit processor. It's powerful, it's cool. It's got CAN built into it, one channel anyway, but it doesn't have an EEPROM. The other thing with Arduino Due is it had these little tiny it had 2 of them, USB ports that I could break one off with eye contact. I didn't actually have to touch it. It would just fly off the board if I looked at it. So what we did was took the basic Arduino Due and we replaced one of the USB ports with these much more robust printer ports, the mini B, and we like soldered them to the core of the board where they're like really on there. And we added an EEPROM. We added a 256K EEPROM because they don't make 4K EEPROMs anymore. That's like the smallest, cheapest one there is. In the case of our solar controller, I can put 57 days of data logged every 5 minutes in that EEPROM. But I really only need a couple hundred bytes, so you can enter what the top voltage is, the bottom voltage, maximum current, maximum temperature. Just it's not 100 bytes, but I need it to be there every time the board comes up. So that's the EEPROM. And then we added the CAN, the controller chip, had CAN built into it, but you have to have a transceiver chip. The controller was in the SAM3X, but the actual transceiver that does the line control is an external chip, and we use the TISN65. It's the best CAN chip out there, I think. And so we put a little green terminal strip here, did away with the little plug-in for the 12 volts, which is going to come off in an automotive environment, vibrate and so forth. So we put 4 screw terminals for the 12 volts in the ground and the CAN high and low. And so we have an Arduino Due that can communicate at very high data rates on CAN bus without any shield. And this has become the center of our operation. Our Delphi DC to DC converter is controlled by a little box that has this inside of it. Has a different connector, has different software. We take the same board and the same little box, different connector, and we use that for controlling Chevy Volt chargers. And we do the same thing, different connector, different little cable, same box, to control a TCCH charger. Different software every time, but the same board. I can use the same board over and over, which means I can buy 100 of them at a time and get them very inexpensively made. And so it's a CAN Due, and that's why we call it EVTV CAN Due. The JevQ is like the super hardened version of that, but criminy, I'm charging $595 for that. I won't tell you what the stupid amount I'm paying for them, but it's because they have all these linear opto-isolated inputs and outputs. There's a DC to DC converter, and it was $35. A cinch connector set and enclosure that's over 100. And it just goes on and on. But you don't need all that for a lot of things. And so the EVTV Dewey, if you want to play Arduino and CAN, this is the board. Now, it only gives you one port. I'd say 99% of our projects only need one port. And so it's just, it's cheap, it's ideal, and it works fine, lasts a long time. And it's been the heart of our enterprise for all of our controllers that were not JevQ. Today, January 25th, I got version duh of this controller in, and I'm really excited about it. We call it the ESP32 CAN Due, and that is because it uses a chip called the ESP WROOM 32 or ESP32. We've been following this Chinese chip for 18 months. It has a lot of promise. Of course, as a Chinese chip, it has a lot of documentation problems. A guy named Andrew Kolb has jumped in. I don't like his writing style. I don't like the depth that he doesn't go to. But he's got a 750-page book on this thing. And there's grown up a community of people developing software for it. Kind of painfully and kind of slowly. But they now have it working with the Arduino IDE. And it's working reasonably well, given that it's really quite different. It's this chip, at the heart of it, are a dual core, two processors that run at 240 megahertz. They're 32-bit processors, just like the SAM3X, but there's two cores, and they run at about 3 times the speed. Speed in computers covers a multitude of sins in software. You can write some really ugly software that does a lot of things it shouldn't do. But with enough hardware, it'll do it quick enough that it'll still look like you know what you're doing. This brings some problems in synchronizing multitasks between the two processors. They're using free RTOS in that, and it's a little bit of a learning curve, but I think that will be useful. Particularly, what we run into is we have a processor running a program, but we also have to mind our communications. I love to do interrupt-driven CAN, where our CAN transceiver detects a CAN message, compares it to a filter, and if it's one for us, it interrupts what we're doing in the program, and we can go process that. That can be problematical sometimes. You get into timing issues with other CAN messages and with other processes. With 2 cores, we could conceivably devote one to communications and the other one to something else. And that brings up the something else, which is communications. And we have on this board enabled 2 CAN transceivers. And this chip doesn't have a CAN controller in it, so we had to do the full controller plus transceiver externally, and an EEPROM, and we did that, and did 2 full CAN ports, and so our 4 screw terminals have grown to 6, but still ground, 12 volts. CAN 0 high and low, and CAN 1 high and low. And so this is a 2-channel CAN board. But the reason we went to this chip was not for the speed and not for the 2 cores and not to get 2 channels, but it does some other magic. This is an antenna, and it has built-in Bluetooth BLE 4.0 and Wi-Fi. And my interest, I could use Wi-Fi for a lot of things, but I'm a big BLE fan. We actually developed with an Adafruit board, a module, and added it to the JevQ, and loved it, except for 3 things. One, it had some operations you call that are blocking. In other words, the whole box stops while we wait for an answer from the NRF Bluetooth chip. 2, for some ungodly reason, we have never been able to get anybody to answer. They had limited it to 30 characteristics total, 30 variables you could manage in Bluetooth. And 4th, the module would get lost and would have to be reset manually, and they didn't bring out the reset pin to the interface. And so we had our very first failures of JevQs, and they were all related to the Adafruit module. And so we quit shipping them with the JevQ after doing quite a bit of development for the Adafruit software module. We just had to quit doing it on the JevQ. But I was very enthused about Bluetooth, just not very enthused about Adafruit's very crippled effort there. They've got a lot of products going and just really couldn't be bothered to focus on that one for more than 15 minutes. We kind of offered Collins assistance to work on their firmware, and they simply declined. And so that's that. But the EVTV ESP32 CAN Due will have full Bluetooth BLE, Bluetooth Low Energy, and that will allow you to be either a controller or a peripheral in that transaction, and a large space for variables. And the interface looks a little crude right now to me. Andrew Cobble's done some C++ objects for him. I'm not real happy with it, but I think this is now open source work, and so not so much me, Colin, can get in there and revise both CAN Due or CAN driver, but probably a Bluetooth driver for this library, for this chip, that will let us do some interesting things. Why am I so on fire about Bluetooth Low Energy? Bluetooth Low Energy is a low latency, low data rate version of Bluetooth. Now, why would I want a low data rate? I don't really care about the data rate. I want low latency. In other words, I send a packet and I get a packet back, and it happens quickly. The packets are only 28 bytes. But what they can do, I can match variables to in my program to Bluetooth characteristics, they're called, under services. And so I can link a Apple iPhone or an iPad or an Android application by Bluetooth to this board and the variables in it. And anytime a variable changes, this board will send a notify to the phone and say, hey, this value changed. And the phone says, hey, give it to me. And this board gives it to them. Now, why do they call it low energy? That's the whole radio transmission. I sent 28 bytes to the phone and said, hey, I got a new value. The phone sends me 28 bytes and says, I'll take it. And this sends 28 bytes And it says, here it is. And that's it. The radio's shut off. It's not low power. In fact, I just got a remarkable device called a digital ant that you hook up to your garage door opener. You don't even have to fool with the 2.4 megahertz or 2.4 gigahertz or 900 megahertz garage door frequency. It uses Bluetooth, and you just hook it up as if it was a button. But now your phone can open your garage door. Well, we got her condo with 2 doors, my house with 3 doors, a gate, and the shop with 4 doors. And we got a dozen vehicles that we drive. Whatever controller I need is in the other car. But you always have your phone with you. And so I can put all those doors on Digital Ant and just flip open my phone to open or close a door. It's a very dumb device. Doesn't sense the door position or anything. It just triggers the door as if you'd pushed a button, a hardwired button. But it's Bluetooth, and it happens right now. I tried it with a door at home and walked away from it. I would say I was 300 feet away, and it was still working, and I got tired of testing it. I never did find the edge. It can do it from anywhere in the house. So it's not low power, it's low energy in that the radio is off most of the time. So you can use a coin cell battery to operate something, and it'll last for a year. That's the low energy. Not to be confused with low power. It's actually a little higher power than the regular Bluetooth, but it operates in bursts. And so we think this is going to be next gen EVTV CAN Due, and it's going to have integral Bluetooth and Wi-Fi connectivity. And what does that really mean? It really means using phones and tablets as displays for all of our controllers. And so I'm very excited about it. This is the first. We got 5 boards in. I sent 2 to Colin immediately. I've got 3, and we're going to start playing with them as this really goes. We'll make some changes, go back to Tony in China, get another 5 made. He'll send them to us. Then we'll see what we should have changed, change it again, and that'll be 4 or 5 iterations at 5 units each. And then I'll order 100 of them and turn them loose. But this, there's a number of ESP32 boards out there. I think they've all gone the wrong direction. This is a small chip, and they're all fascinated with the Internet of Things and with the success of teensy. So what they do is they put it on a card with no USB port, with no power supply. You have to provide 5 volts, with nothing. And it's small. They'll be this long and this wide, but you can't do anything with them. To wire to them, you have to build a socket or a breadboard or solder wires to it or something. This is exactly the same form factor as our Arduino Due. In fact, our Tesla BMS shield will plug right into this. We lose the pins at the end because I need this antenna to hang out here. The ESP32 has much fewer digital inputs and outputs, but they're much more flexible in their assignment. And we never used more than 3 or 4 inputs and 8 outputs ever on any of our devices. But we always like to program it with a USB port. We want to work off 12 volts. I don't care about 5 volts. We don't have 5 volts in the car. The 5 volt regulator is in the board. We hook it up to 12 volts automotive and ground, and we have 2 CAN ports, which again are kind of vehicle in nature. And so if you're interested in getting into Arduino development, or if you already do that, this board, I think, is going to be a big deal for a lot of people, and it's because of the form factor and what's included. It's an Arduino Due, but with CAN ports and now Bluetooth and Wi-Fi. But these pins are all the ones you expect. Some of them aren't connected to anything because we don't have that many pins on the ESP32. We put all the sockets so an existing shield would plug into it. But a lot of the pins don't have anything going to them. You have to use the pins that do in your software and with your shields to make it work. So it's not a Arduino clone, but it's a similar form factor and lets you do shields that are, you know, substantially the same. Some shields could actually be made to work, but you can design shields that work pretty well. As long as they don't require 51 pins to operate them, you'll be okay. And so I'm working on a book about this. We're gonna have a lot of documentation, examples, and we will have them in the store. I don't know what the pricing is going to be. I don't know what they're going to cost me till we get done with the design and make 100 of them. But it should be similar to the EVTV Dewey. So that's got me pretty excited. Colin and I are going to be playing with that over the next couple of weeks and seeing if we can get something going here with some smartphone apps, which will be interesting. He only does Android and I only do Apple, and he doesn't want anything to do with Apple, and I really don't want anything to do with Android. They just fall into two different camps there. But I think this using the Arduino integrated design environment is a big plus and is familiar to a lot of people and will let us do some pretty serious communications between CAN, Bluetooth, and Wi-Fi. And so I'm very excited about the board. Stay with us. We'll be back. In the Arduino integrated design environment, or IDE, and one of the big things that I'm interested in the ESP32 about, or any chip, what we look for is not so much the chip features as the culture, the environment, the cult that builds around it, the number of people that are involved in it, contributing software, documentation, examples, and so forth. And that's basically what we've been waiting for and observing on the ESP32. It has its own IDF interface, design functions, software that works under GCC, C++, and that's all well and good. Our people, and I think a lot of people, like the Arduino IDE. It is not nearly as fully featured as almost anything out there. The most popular, I suppose, is Eclipse. But it has some things to recommend it. One, it's free. You just download it. Two, it's very easy to install. And three, it's very simple and easy to deal with. And it's become quite extensible as far as adding different boards and board variants. So it's kind of least common denominator, but I like it. Of course, I did assembly language for years with a basic text editor. It took an armed assault vehicle to get me into a simple assembler. So I tend to be a little bit minimalist anyway in the tools. I want to know what the tools are doing. I don't like programs that do things for me very much. The Apple's Xcode drives me crazy with all the stuff it tries to help me with. Windows, I just don't do anymore. It's the same thing every time I go to do something. It wants to know if I really want to do that. And so the IDF is, or the Arduino IDE is a big part of it. We also look for other people taking an interest in the chip. And there's literally dozens of YouTube videos right now on different things you can do with an ESP32 and things that people are doing. I think most of them have not delved very deeply into the how-tos and so forth yet, but the interest is there, and people are making videos, and they're learning to program this chip. And the more you learn, the more you like it, basically. It's really quite powerful. When I say it's 2 cores and 240 megahertz, let's give that a little context. A guy built a benchmark program, I can't remember his name, in 1977, kind of concurrent with the introduction of the Digital Equipment Corporation VAX 11-780 mini computer. And that was an entrant, kind of to take on the venerable IBM 360 sort of mini mainframes. And there was a floating point benchmark system out there called Whetstone. And so he called this Dry Stone. And it does, instead of floating point operations, integer operations. And the VAX 11780 and the IBM 360, the benchmark was actually designed so they would be the base at 1 million instructions per second using this benchmark software program he wrote. And so we call that today a dry stone, million instructions per second, or DMIPS. And by the way, it's still used. It's kind of falling out of favor in the face of the iPhone, iTablets, and so forth, because they have so many things going on with GPUs and so forth. But for a basic processor, the dry stone MIPS, or DMIPS, is to this day kind of a benchmark. I would point out that this little Tensilica Extensa ESP32 chip does 600 DMIPS. That's what it's rated at. That means in a $2.40 chip, we have the computational equivalent of 600 IBM 360s, or 600 DEC VAX 11780s. Now, a lot of you guys have got shirts older than you are, so this doesn't mean a lot, but it's absolutely astounding to me the progress, or the light years we've come from what we considered very advanced, top of the line computers in 1977 to where we're at today. A personal computer was a tiny little calculator chip computer that you were not going to have the processing power of a mini computer, but hopefully you could do some things with it. Now, this isn't even a desktop computer. It's a microcontroller, basically, that you put in devices. You would stick an ESP32 in your refrigerator, your garage door opener, and so forth. It's a multi-controller, but it has 600 times the processing power of a VAX 11780. And I guess I've grown out of my time. because this is just astounding to me. So we're going to do a series of a little mini videos. I know you're already accustomed to my 2-hour videos. I'm going to attempt to do more videos and smaller ones on the ESP32. Little 10-minute blurbs on how to do a particular function. In order to teach you how to do it, I have to learn it. And there is a significant learning curve involved in moving from the SAM3X Arduino DUI to the ESP32 Tensilica Extensa chip. It's actually quite a bit. All programmers do this. You basically develop a toolkit of your little techniques that you can't live without. And I mean, going back to assembly language, first thing you do is do a little routine to print stuff to the screen, and then you start using that to print stuff to the screen. You almost build your own language. But no matter how high a level language you go to, there's just certain things you want in your environment, and you want and things you have to do over and over again. Of course, a lot of ours revolve around CAN. In the future, a lot of them will revolve around Bluetooth. But simply saving our persistent variables, the things you need to stay there between sessions, is something that I developed the way I do that. It's a structure. I save it to the EEPROM, or in this case, non-volatile static RAM, and so forth. So there's just little routines that you use in cookbook recipe fashion after you've developed them. And so I'm going to do, as I build my toolkit, I'm going to do a little series of mini videos on how you do various things to program the ESP32, and hopefully in that way contribute a little bit to that community or that culture. Help Neil Colban, I got his name wrong earlier, I'm sorry, Neil. He's actually done some fabulous work with his ESP32 snippets on GitHub, and that's what's brought us Wi-Fi and Bluetooth and so forth into the Arduino IDE, and he's done more than anybody to advance this chip, and he's an extremely bright guy. His book is it's better than I portrayed it, but it is big. It's up to 750 pages, so he's put in a lot of work on this, and we're going to help. I'm going to contribute some code to his snippets, and probably do some documentation and some videos, so he doesn't feel like the only savage on the buffalo hunt, and that's essentially the thing. Here is a little function that we just have to have, and that's a watchdog. And I actually did a video on this using their very capable timer set. The ESP32 actually has 4 timers, and you'll be delighted to learn they're 80 megahertz. That gives you about 12.5 nanoseconds of strike, and so you actually have to divide it down, and it allows this by 80 to get it to the point where it's a microsecond account. And so this opens the door to some huge things, particularly when you want to do pulse width modulation. We want to do a 3-phase controller or something and have 3 I/O pins doing a sine wave to drive a motor or something. To be able to get down to this time level is incredible. So I actually mapped out a watchdog timer video using their timers. Colin then pointed out, well, they've already got that built in. So, again, these are going to be small videos on very little programming code, just enough code to demonstrate it. And in this case, it's trivially little. Speaking of tools you just have to have, I just have to have, this is a little template class for streaming text and variables out the USB port, so I can see them. In Arduino, they typically use serial.print and then some stuff in there, or serial.print line if you want a carriage return on it. And it does do some basic formatting of variable numeric displays. If I want to do formatting of variables, how they're displayed, there's a much more advanced function in C++ called sprintf, and you can basically load up a buffer with text and variables and format the variables and so forth, and then just send the buffer out the port. But for quick and dirty printing, I don't want to do any of that, and so this template lets me just stream stuff out the port with this double left character. And here is a example of that. Is our last line of the program: serial, the double character, a literal string, a double character, a variable, the character, and some more string. I know how to send a line feed or carriage return out of serial port. We just use \n as the escape character and the character for a line feed. So instead of having a line for each of these things, I can just put it all on one line, and with the caret symbol, it's called streaming in C++. So every program I do in Arduino uses this. In GCC, you actually already have streaming, so you don't have to do this. But this is a little trick to let me do streaming in the Arduino IDF. I'm going to set up a long variable here called loop time and initialize it to 0. That's a global variable. I can get to it anywhere in the program. It's long because a built-in function called millis is a long. And millis returns the current runtime, how long you've been up since powering up, in milliseconds. And we're going to use that in a little bit. We need one library, ESP task WDT, which is watchdog task. They have two types of watchdogs already built for you: watchdog task and watchdog interrupt. This is what you would use in a program running on one of the cores in a task, and so we include that library. It's required here. All Arduino programs, of course, have setup and loop. In our setup, we initialize our serial port. This is our USB port on our ESP32 CAN Due board. I'm going to set that to 115,200. Actually, one of the delights of this ESP32, I think we uploaded 982. Here's our, to do this, you just select that board, ESP32 development module. We'll probably have a EVTV ESP32 CAN Due board thing, but right now this works fine. And the flash frequency is 80 megahertz, but upload is at 921,600, and so this USB port's some faster than we had available before. And so I could actually set this, and have done so, set the serial port for 1 megabit per second, and it'll work fine. Don't need it here. In setup, I'm going to say that we're give myself a line feed and say setting watchdog in setup, and then a couple line feeds. That's actually a little bit important. You'll see why in a little bit. Here I'm initializing the watchdog, and what I'm saying here is that we're going to set the watchdog time period, the alarm time, at 3 seconds. Unlike my timer version, which you can do very precisely, their built-in watchdog function is only available in around seconds. That's not a problem at all. And true means that it'll go into panic mode, which does a core dump when it triggers. And then we add it. Subscribe this task for the watchdog. What is a watchdog? A watchdog is a puppy that you have at your house that anytime someone comes to the house, it will bark loudly, alerting you that you have a visitor, maybe perhaps a known visitor, and perhaps not. And so it's a watchdog. Similarly, software, and particularly these multi-controllers, I know that 100% of your code is guaranteed perfect and glows in the dark and will never fail at all. On the other hand, I'm somewhat inept. I've been waiting for something to load, something to save, or something to print since 1979, and I have yet to write a bug-free program or one that didn't have some problems. Also, in the environment we operate in, we're subject to a lot of noise. And it can cause the microprocessor, in this case the ESP32, to jump track. And particularly the ESP32, we're going to have Wi-Fi going, USB, Bluetooth. We use free RTOS, 2 cores. I guarantee you it's just going to get to a situation where the processor basically just locks up. It gets lost, overruns a buffer you have set up or something, and it just locks up. It quits operating. Not good if you're going down the road at 70 miles an hour, depending on this thing to do something for you. And so we want to be able to recover from a computational disaster, basically. And we use a watchdog basically to reboot it, reset it up, reinitialize, and start all over. And so what this 3 seconds is, if we don't feed the watchdog, if our software does not reset the watchdog, sometime within 3 seconds, it's going to reboot the computer. And in fact, it's going to do a core dump and show us what was in there. That's called panic when it does that. And that's the end of our setup and all the setup we need for the watchdog. Here's our main loop. And the first thing we do is ESP task WTDT reset. What does that do? Well, that resets the timer. And by the way, it uses the same timers as my other program did. This is just configured for you. To 0. And so we get another 3 seconds when we hit this. And then I'm going to copy millis, our current runtime, into loop time. That's basically I'm setting up a time mark, a time stamp for right now where we're at. And then I print to the screen that the main loop is running and a carriage return. And then I delay and delay is in milliseconds, so I delay for 3,000 milliseconds. Well, that's about 3 seconds, isn't it? And then I say that loop time equals millis, our current run time after the delay, minus loop time, which is our timestamp we set up here. And so that's going to give me the time from here, this point, to here. And then I'm going to print that on the screen out my USB port using my streaming template, time in loop, and the new loop time and milliseconds to carriage returns. So let's see with my window here. Let's compile and upload that, and I can press that right arrow and it'll take it, and it's compiling the software, and now it's flashing it to the thing. It says board resetting, so we'll reset and we're up and running. And the first thing we do is show some variables. We're setting our watchdog in setup. Our main loop is running, and our time in the loop is 3,000 milliseconds. And then we loop again, and we say main loop running. But bada boom, bada bang, we didn't set this up. It says task watchdog got triggered. The following task did not reset the watchdog in time. Loop task, the CPU 1. Task currently running, CPU 0 is idle, and CPU 1 is loop task, and that's our program, and it's aborting, and it was called at this address, and then here's your backtrace information, rebooting, and the time. So from here to here, I didn't program any of that. That's all information from the watchdog task function or method that it's providing me. And here's our panicked dump of information. And but hey, we're starting up again, and it says setting watchdog in setup. Well, that's the beginning of my program. Main loop running. I go into the loop. Time in loop is 3,000 seconds, 3,000 milliseconds, and main loop's running, and we triggered again. And so we're not feeding the dog often enough. We have 3 seconds set, but I've got 3 seconds in the delay, and it takes some time to do all this looping. Let's change this to 2,999 milliseconds and see if that makes a difference. And we'll recompile and reflash our software to the and this is one of our prototype CAN Due boards. And let's bring it up again and see what happens now. Main loop running, time in loop 2999 milliseconds. Main loop running, time in loop 2999 milliseconds. Main loop running, time in loop 2999 milliseconds. And we just keep looping in our main loop because we're under the 3 seconds in the main loop. See, we're resetting that watchdog here with each iteration through the loop, and we're timing that, and we put in a delay. We print out our time so I can see how long it's going, and we seem to be effective here. Let's change this to 3001. Recompile. Bring up our serial monitor. This is showing our USB port. Well, we're just basically getting through setup. We get our main loop running, but we time out before we ever even print anything. Print the time. We're timing out in delay because we have it set up for 3001 milliseconds. And so our watchdog works, and we can use this. Of course, you don't need all my little display stuff. Here is your watchdog setup critical items, and that is you have to include the library. you have to establish your watchdog time, and you have to add it to your task. And then somewhere in your software loop, you have to feed the watchdog. We call that feeding the watchdog. It's basically resetting that thing. And so as long as you reset it before your expiration time, you'll run, and the watchdog doesn't do anything. It doesn't interfere with your program in any way. But if you lock up and fail to do that reset within 3 seconds, you get an interrupt, and it will reboot your computer, go back through setup, and go back into your loop. So that's all you need, is this line where you reset it, these two where you configure it, and this library to add it to your program. Stay with us. Alright, we're going to take a look now at a gentleman named John Arkless of New Zealand. He was a friend of Nick Smith's, and he embarked in September of 2015 on a build project using an Audi TT. The Audi TT is based on the Volkswagen new Beetle chassis, but it's a much slicker, sportier body style. I would say that it's the a Carmen Ghia, as the Carmen Ghia was to the original Beetle. The Audi TT is to the new Super Beetle, and it's a marvelous little, very sporty sedan, and I think an ideal candidate for a build. He procured from us a Siemens motor with DMOX 645 controller, our JEVQ, Generalized Electric Vehicle Control Unit, and the Andromeda Systems EVIC display, along with a bunch of other parts, of course. And started his build. He has a life on the side, and so it's going on for a little over 2 years, but he's enduring some success at this point. Let's take a look.
A quick walk around of my Audi TT electric car project. Been underway for 2 years now, and I'm probably 80% complete. So here's the beastie here. So we'll start from the back of the car with the AC charging point. Let's dive inside the car here and open the fuel filler and the tailgate at the same time. So the charging point is integrated into the fuel filler position. It's quite a nice job, if I say so myself. And that's a slow AC charging, 3.3 kilowatts maximum. So you also use the public charging infrastructure here in New Zealand. Quick shot of the electric badge. It's a bit garish in gold. I might spray it blue, I think, maybe. Okay, so at the back of the car, that's quite a large battery pack there. 6500 ampere cells in there, about 200 kg in weight. And my philosophy around locating the battery pack was to keep the mass central inside the axles as far as practical. I wasn't so concerned about maintaining a low center of gravity, as that can be countered with stiff springs and anti-roll bars. So, well, there you go. It may work, may not. That's the DC-DC converter right there. So 320 volts down to 12 volts. Not actually secured at the moment. Just have to find a location for it. Probably in the wheel well. I'll sacrifice that. And other than that, the boot space is actually reasonably similar to the original, so I haven't sacrificed much boot space, which is nice to have. Okay, from the AC charge inlet. You see the orange cable going out there under the battery pack, and then ends up at the charger, obviously, which is actually located under the car in this enclosure here. So it's a Bruce 3.3 kilowatt charger, air cooled, hence the inlet on the, as you can see on that side, and on either side of the enclosure is an outlet ducted to the underside of the battery compartment. So having heating for the battery in cold weather is a good thing. So that worked out quite nicely. You can just see the Bilstein suspension on the back, height adjustable. Now, following the HV cables from the rear battery pack, I've got the HV control contactors fusing here under the car. So this is actually negative contactor here. There's no voltage on at the moment, obviously. This fuse here is for the auxiliary equipment, being the cabin heater and the DC-DC converter. And in the identical enclosure, forward is the positive contactor and the pre-charge resistor. And then out to the front battery pack and the converter. That's what lives under here. So these are actually mounted in cast aluminium IP68 enclosures, as they're going to have to survive some pretty harsh conditions here, road spray, etc. So I think they'll be quite happy in there. There are some you probably can't see, maybe you can. There's a couple of vents in there, which they're IP69K vents, which will maintain the pressure the same as the external atmosphere inside the enclosures, so there's no chance of any seal failure due to the vacuuming of the enclosure when the things cool down. Okay, so front of the car. Obviously the front of the car's quite complete, but you can see stuff in that way. That's the early generation Nissan Leaf water heater, 4 kilowatts. There's 3 IGBT heater elements in there, sorry, 4 heater elements, total of 4 kilowatts. That'll be controlled from an Arduino controller, as we don't have the Nissan Leaf computer to do the control for that anymore. And the original radiator, which I'm probably not going to retain. I need to have 2 separate heat exchangers on this car, one for the water-cooled motor, one for the water-cooled inverter or motor controller. So I'm probably going to replace that with 2 high-efficiency heat exchangers in the same space. Okay, and on to the side of the car, the driver's side of the car. Housed in front of the front wheel arch is the power steering pump of a Holden stroke Vauxhall Astra. Fits in there quite nicely, and you can just see the HV cables coming down from the controller to the traction motor itself, which is, as mentioned before, water-cooled 3-phase AC Siemens unit, mounted to standard Audi 5-speed manual gearbox via an uprated clutch. Okay, so let's pop the hood. So under here, shoehorned is the front battery pack, 35 cells in here. So which it comes a total of 100 cells, 100 amp hour cells. So The entire battery pack, traction pack, is 32 kilowatt hours, 320 volts. There's the two bulkhead connectors. So the battery box actually comes out pretty easily to service any component underneath there if required. Not a lot else to see here, I guess. This is the fuse disconnect. Part of the regulations here in New Zealand is to have a separate fuse disconnect for every battery pack, so you'll see the one in the rear in a few moments. That's the front one. This is the surge port for the water heater, and this box here is incomplete, but is the relay control box for all the low voltage EV control stuff. Okay, so a quick look inside the car. So a previous video of mine showed the control procedure for starting the car, which is this engine stop start push button here, there's an e-stop here. So mounted here will be in place the original radio is a 7-inch EVIC touch screen display, and that's pretty much all the space allows for there. Unfortunately, the radio has to be relocated somewhere else, which is another high priority for me. And the auxiliary Arduino controller, which will do the control work for the water heater and probably some other stuff as well. So it's obviously yet to be completed and mounted in the car. Okay, so it's almost drivable. I haven't turned the motor yet, but I expect to do that within the next few weeks after a trip to the States due to take. And I'll be, after it's motor spun up, there's a few more components to add. There's a fuel gauge driver there, which will drive the fuel gauge. It's a coulomb counter, and we'll also drive the tachometer to show instantaneous power usage. Sounds nice. And that's a Hella vacuum pump EP30, which for the brakes. And pretty much the heart of the system is EVTV JevQ6 controller, which looks like a bit of wiring, but it's actually pretty simple to implement. Not all of those cords will be used. So that's the next step in the project, is do some wiring and some testing. There you have it. So 6 months time, I'm hoping it'll be pretty much complete and hopefully on the road. Thanks for watching.
Okay.
Cool.
That's good. I might at some point give it full throttle. Just be aware. It's clear to go.